So Oscar, you think we can start?
Yeah, I think so.
So, okay, let's start this session. Good morning or good afternoon, everyone. It is a great pleasure for me to open this parallel session of the 16 Marcel Grossman meeting on the nature of the galactic chaos. First of all, I have to inform you that the session is recorded and it is assumed that all participants automatically give their consent to do so. So the schedule, you can see the schedule of this session. We have 6 talks. The first one is by Jonas Chavez Montero of the Donostia International Physics Center on a nearly complete census of intergalactic gas using the kinematic Sunyaev-Zel'dovich effect. The second one is by Sara Recchia of the University of Torino on giant cosmic ray halos around M31 and the Milky Way. Then there are 4 talks by our collaborators or young students. The first one is by Lindita Molli of the University of Tirana on primordial black holes as dark matter candidates in the galactic halo. Then there is the talk by Antonio Franco of the University of Salento about searching for intermediate mass black holes in the Milky Way's galactic halo. Then Nora Steyer by University of Salento on virial clouds evolution 1 from the surface of last scattering up to the formation of population tree stars. And the last talk will be by Mohammad Bilal of the Abdus Salam School of Mathematics on the analysis of the velocity rotational curves via Weyl interaction modified gravity. I just ask you to be in time since we have to follow the schedule as closely as possible. If there will be not enough time for discussion at the end of each talk, we have about half an hour at the end of the session after the last talk. So I would like to ask all of you to remain to remain in the session until the end. Okay, so let's start with let me unshare now. Stop sharing my screen, and I ask to Jonas to share his screen, so you can start your presentation. Thanks.
Okay, now
yes,
you should be able to see my first slide and change the slide. Is that okay? Perfect. Okay, so my name is Jonas Chavez Montero, and I'm a postdoc at the Donostia International Physics Center. I would like to start by thanking the organizers, Francesco and Asgar, for inviting me to this session, giving me the opportunity to present my latest findings about the location and abundance of intergalactic gas. You can find this in this recent paper, and you can see here my collaborators. But let's start with a brief introduction to the problem. So as we know, the composition of the universe today is mainly dark energy and dark matter, and we have around a 5% of, around a 5% of baryons. We only know the true nature of the baryonic matter, and the nature of dark energy and dark matter is still a mystery. But I think that just because of that, we usually assume that all the baryonic matter were under control at all times, but that's not really the case. So in the early universe, we know that all this matter was hot and dense and was emitting. And we can see this in the CMB, all these different anisotropies that are coming from this really hot matter. By looking at the CMB prediction from Big Bang nucleosynthesis, we can put strict constraints on the abundance of baryons in the universe. However, the physical picture is completely different at late times. Most of the universe is empty, and we can only observe galaxies and maybe the gas surrounding these galaxies in a more or less straightforward manner. So Most of the cosmic gas present intermediate temperatures and density is much more difficult to observe, and such is the case that until recently, around 30%, 40% of this gas was missing. What I mean by this is after accounting for all the gas in galaxies and in the galactic medium, intercluster medium, and the gas that we can detect outside galaxies, still 30% of the gas was missing. And this is the so-called missing baryon problem. And now recent studies are starting to discover that this gas is more likely to be in the intergalactic medium. So for example, a recent paper from Carlos Hernández Monteagudo discovered using the pairwise Kinematic Sunyaev-Zel'dovich effect and Planck data that around 50% of the baryons were surrounding SDSS galaxies. So this is what I'm showing here in this bottom right figure, that you can see that the baryon fraction as they were opening the aperture around SDSS galaxies was increasing and reaching more or less at 50% of the amount of baryon that we expect from early universe observations and predictions. This other paper from Nicastro 2018, using a completely different technique, deep X-ray observations, was discovering that along the line of sight of a quasar, there were different systems that were not linked directly to this quasar. And most likely this was gas that they were detecting and that was in the intergalactic medium and in filaments. Another set of works use the thermal Sunyaev-Zel'dovich effect to detect this intergalactic gas. In this case, these two papers that came out more or less at the same time, using this effect to discover gas that was between pairs of galaxies. So you can see here, you have different Bose galaxies, and there is something in the middle that is more likely that is intergalactic gas that they were detecting. So all these different works, they are pointing out that this 30% of missing baryons is really in the intergalactic medium. But these works were just studying either a few recifs or a reduced number of line of sights, so a complete picture of all the cosmic gas at late times is still missing. And of all these different methods, what I'm going to use now, I'm going to present my study of using the Kinematic Sunyaev-Zel'dovich effect to detect this gas. So what is the KSZ effect? This is the Doppler boosting of CMB photons as they scatter off a free electron moving relative to the CMB rest frame. So these electrons are introducing a thermal anisotropy in the CMB that is proportional to the amount of electrons that we have and the velocity of this. So we have to imagine a cloud of electrons that is moving relative to the CMB rest frame, and this inducing an anisotropy in the CMB that scatter off this region. So if this signal is proportional to all baryons that are moving relative to the CMB rest frame, we will, in principle, we could be able to detect all the baryons in the universe because we know that almost everything is not at rest. But the problem is that detecting the KSZ effect is very challenging. And this is because the spectral shape is very, very similar to the spectral shape of primordial CMB anisotropies. Only if you go to the introduced relativistic corrections, you have a shape that is slightly different, otherwise it's exactly the same. And on top of that, primordial anisotropies present an amplitude of around 100 times that of the KSZ anisotropies. So the signal is very small. The spectral shape is exactly the same as the primordial CMB, and on top of that, some technique needs to note the velocity field of intervening matter in order to extract this effect, and it's very difficult to detect this. So here in this paper, what I propose is we propose is a new method to detect this the KSZ effect. That is the cross correlation of angular. Sorry that I'm changing this, otherwise I can see anything. That is the cross-correlation of CMB observations and angular redshift fluctuations. So what is angular redshift fluctuations? What we did is to project the redshift field of the galaxies, so just the galaxy redshifts, into different cells and then remove the monopole from this observable. So the idea is that the redshift of a galaxy is proportional to the redshift coming from the Hubble flow, and another component that is proportional to the velocity, the peculiar velocity of the galaxies. There are other components, but these are the most important ones. And what we did is to select galaxies according to a radial selection function. And what we found is that for broad selection functions, this observable is sensitive to the density field. But for narrow windows, is proportional to the velocity field. So we can see this even by eye in the right panel. You have angular redshift fluctuations in the top panel and the velocity field in the bottom panel. And this is coming from a simulation. So what I did is to project these two observables into a redshift cell. And what you can see even by eye is that on large scales, you have these fluctuations that look really similar. So we can see this even by eye, but more qualitatively, when you compute the cross correlation of the angular redshift fluctuation and the KSZ effect, you find that these are correlated on large scales in the linear regime up to a multiple. This is for redshift 0.5, and this is above 0.5, the cross correlation up to a multiple around 500. So the KSZ effect is proportional to the velocity field, angular redshift fluctuations are proportional to the velocity field, and we are going to use the cross correlation to detect the KSZ effect. So yeah, let's go directly and use data and try to extract this effect from observations. So what I decided to do is to use foreground reduced plan maps. So the idea is that there are different techniques to clean these maps from systematics. and thinking about dust and other types of contamination from our galaxy. We use all these different maps that use different techniques to remove this contamination, and then like structure tracers to create the angular redshift fluctuation maps. In this case, 6DF galaxies are low redshift because they were covering 50% of the sky. At higher redshift, Bose galaxies that were covering 25% of the sky, and at even higher redshifts, SDSS quasars up to redshift around 5. But what I was saying before is that we have a problem here because primordial CMB fluctuations have the same spectral shape as the KSZ signal. So in order to reduce the contamination from primordial CMB fluctuations, we applied an aperture photometry filter on the position of all the galaxies that we consider to create the angular redshift fluctuation maps. So we are going to use these galaxies as tracers of the intergalactic gas. Aperture photometry works as follows. You select a certain circle in the sky and then an annulus, as you just remove the signal from the annulus from that in the inner circle. In this way, what you do is to remove all the fluctuations that are constant across the aperture. In this way, you can remove all the CMB anisotropies that are constant over that aperture. So yeah, just in summary, what we do is to create first this aperture high pass filter CMB maps that we take the foreground reduced maps from Planck. We take different tracers of the gas. In the position of all these tracers, we apply aperture photometry with different apertures. In that way, we capture all the gas that is around, inside a certain aperture around the galaxy and create one map. Then we use a similar approach. We select the same galaxies that we use to create these maps, these CMB maps, to create angular redshift fluctuation maps that are proportional to the velocity field in the same way that the other maps are proportional to the velocity field. And finally, we cross-correlate these two maps in order to extract the KSZ signal. So these are the results just for two different apertures, two different redshift cells. On the left panel, we have the results for both galaxies at redshift around 0.6, and in the right panel from quasars at redshift around 4. So as you can see, we only have signal on very large scales, as we were expecting. And as we move to higher redshift, the signal is, we can see signal up to higher multiples, and this is because the same multiple corresponds to a higher, to a larger scale, because we are going to a higher redshift. The symbols are showing the results for different, coming from different foreground clean CMB maps. As you can see, all the symbols are very similar. What this means is that the foregrounds that are not cleaned by these different procedures are not affecting a lot our measurements. Everything is within the error bars, or well, and closer. And the dashed line is showing here the best fitting model that we have from perturbation theory, because this is the signal is just here on very linear scale, so we can use perturbation theory to describe it. As you can see, it's giving a good description of the signal. So after doing the same and computing the cross correlations for different apertures, we consider between 3 arc minutes and 50 arc minutes, and all these different redshift cells, we consider 16 redshift cells between redshift around 0.08 and 5. We detect, and after accounting for all the cross correlations, we detect the KSZ effect with a significance of around 11 sigma. Until now, the only thing that we were doing is cross-correlating maps, so we were not assuming anything. But now we want to extract the KSZ optical depth that is proportional to the amount of gas generating the signal. And in the end, it's giving the amplitude of that template that I was showing before. So in order to do that, we need the cross-correlation of the maps that we already have, and a covariance matrix that I estimate using a cross-correlation of real angular redshift fluctuation maps and simulated CMB maps. So I simulated 1,000 different CMB maps, and I put all of them through the pipeline. And for all these maps, the signal that I was detecting was 0, because I was not including any KSZ effect, and the signal was compatible with 0. And in that way, we can use those maps to generate the covariance matrix. And finally, we also need one template that is coming from linear perturbation theory. So after extracting the KSZ optical depth from all the aperture and all the redshift cells, this is what I find for the maximum one that I find in each redshift cell. So now the symbols here, what I are showing is each symbol, so the result for a different redshift cell, in this case, the maximum KSZ optical depth. The error bar is showing the precision with which I can get that measurement, and the size, the distribution around the symbol is showing you the results from different foreground reduced Planck maps. So as you can see, the signal is showing an evolution that is compatible with these two different lines that are assuming that all the baryons in the universe are emitting in the, well, inducing KSZ anisotropies. That will be the dashed line, and the black dashed line, and the red dashed line is showing the result for 50% of all baryons. As you can see, the results are following that very nicely. So the idea is that now we have measurements of the KSZ optical depth at different apertures at the same redshift. And what I was saying before is that these different apertures are, as you go and open the aperture, you are get more and more intergalactic gas gets into this aperture. So the idea now is to use different measurements from the same redshift in order to set constraints on the properties of the intergalactic gas. So what we are going to do here is to forward modeling the signal. So we are going to assume a certain profile, in this case a beta profile, controlled by a couple of parameters that are giving the amplitude of the profile and the size of the gas clouds. And we are going to forward model this because by using aperture photometry, you are always removing some of the signal that is coming from gas that is farther away. So after doing this, we're going we are going to use an MCMC, but using an inference in order to set constraint on the parameters controlling these profiles. So this is what I'm showing here. The dots are measurements of the KSZ optical depth from different apertures at the same redshift. So in the left panel, I'm showing the result for galaxies at very low redshift, and the right panel for galaxies are ranging around 0.6. So each point is a different measurement from a different aperture, and the orange dashed line is giving you the best fitting model to this signal. So again, what is happening is that first you start to open the aperture and more gas gets into the aperture, contributing to the signal, and to some point, no more gas is entering the aperture and the signal is going down. And this is shown by the also by the data, and we have the results for 16 different redshift cells. And we can put constraints on the properties of this gas profile that is given by the dot dash green line, and you can see here the amplitudes and the size of the different profiles. Okay, so after doing this for all the different redshift cells, this is what we found. In the top panel, what I'm showing is the fraction of all these gas that we detect within collapsed structures. Collapsed structures, what I did here to be really sure that all this gas was outside halos, what I put is that what I did is to integrate all the gas outside 1 megaparsec from the galaxies. The average size of the virial radius of these halos is around 0.2 megaparsecs. So I was completely sure that all this gas was outside halos. And what I was detecting is that more than 99% of this gas for almost all redshift cells, not for the one at very low redshift because the scales are much smaller at low redshift, so I was not able to observe well outside the halo. But for all the other different redshift cells, more than 99% of the gas was outside this inner megaparsec around the sources, so really in the intergalactic medium. So that's the first important result of the paper. And the second one is that the average density of this gas ranges from 10 to around 200 times the cosmic average. And this is compatible with predictions from hydrodynamical simulations. So this is again pointing to the fact that all this gas is really in the intergalactic medium. Finally, what we did is to compute the total amount of gas that we were detecting at all these different redshift cells. So here in this figure, I'm showing the fraction of baryons that we tested relative to the predictions, observation from the early universe and prediction from Big Bang nucleosynthesis. What we find is that we detect around 50% of all the baryons. By the way, this I didn't say it before. These symbols that are in gray is for the cells that we don't detect a significant KSZ signal. For most redshift cells that I was saying before, we detect around 50% of the baryons that we expect from the early universe. By combining this with all the baryons inside galaxies and in the galactic medium and intracluster medium, this will go back to the early universe prediction. So all the abundance of baryons comes into agreement. For very low redshift and very high redshift, you can see that the symbols are far from the 50% line. This is because the abundance of objects that we have at those redshifts are very small. At low redshift, we are only using here very massive systems. At a high redshift, the number density of quasars is very small. So what we did is to fix the properties of the density profile and increase the number density of these objects and do simulations to check if we increase this number density, if we were able to recover all the baryons that should be there. And in fact, this is what we find is signaled here by these triangles. These are above the 1-to-1 relation, but this is just because we were fixing the properties of the profile, and we will expect to change a change in these properties because here these are the most massive systems. So yeah, so in summary, we were able to detect almost all the baryons in the intergalactic medium, and if we combine this with all the baryons in collapsed structures, this is going back to the prediction from the early universe. Just to summarize the talk, what we used was the cross correlation of CMB observations and angular redshift fluctuation, that is this new observable that we came up with, and we found substantial detection of the KSZ effect from redshift 0 up to redshift 5. Then we use different measurements of the KSZ effect from the same redshift in order to set constraints on the properties of the KSZ gas, and we found that this gas resides in the intergalactic medium and account for nearly half of the cosmic baryon. And if we combine all this gas with that in collapsed structures, we have results that are compatible with CMB and Big Bang nucleosynthesis predictions. Yeah, that's all.
Okay, Jonas, thank you very much. Yeah, Asgar, you can go on if you want. Thank you very much for your very interesting talk. I think your results are very important. So I open the discussion. Anyone want to ask any questions or comments on Jonas' talk?
If you have
Okay.
no comment, I would like to just say something. We check is the impact of, okay, let me share again. Because we wanted to check whether the impact of synchrotron emission and gas emission was important on the results. What we also did is to this is the result for the same redshift cell coming not only from foreground clean maps but also for raw maps. And as you can see, the results were really similar, even using raw maps, up to a frequency of around 353 gigahertz. That for those frequencies, the contamination from dust was really important. But for all the other different maps, the results were really similar. So we are sure that the impact of systematics is very small on the results.
Okay, good. Jonas, I would have a curiosity. You showed a plot with KSZ optical depth, which increases with increasing the redshift, right?
Yes.
Yes. I mean, is this correlation related to a correlation between the gas temperature and the redshift? So you find in different redshift shell different gas temperature or not?
The KSZ effect is not directly sensitive to the temperature of the gas. Is proportional. You let me 1 second go back to this slide. It's proportional to the number density of electrons that you have in your gas cloud and the velocity of these electrons, but the bulk velocity of all the cloud, not the inner velocity of the cloud. This is slightly different. So what is really happening here is that the number density of, the density of the universe is increasing towards higher redshift. So we go to higher redshift, this is growing as 1 plus z, and this is more or less what we are showing here in this plot.
Yes, and the other conclusion is that not more, let's say, of about 50% of the baryons, or I mean, most of the baryons cannot be confined within the galactic halos, right?
Exactly. Yeah, when we do, we can see here, for example, in this figure, even by eye, that this is the best fitting gas profile in the green dashed line. As you can see, this is extending well beyond the typical size of the halo that will be here around 0.5 megaparsec. And this is extending up to 8, even 10 megaparsec. So these are gas clouds that are surrounding these halos, but are not. This gas is not directly inside the halos. So the physical picture will be that you have a filament there that is extending well beyond the halo, and you are starting to detect what is in that filament. Here we are assuming something spherical because we don't have a way of just tracing this in 3D, but that will be the physical picture that we are detecting the gas in filaments.
Okay, thank you very much, Jonas. Very interesting.
And thank you for the questions.
Is there any other questions? We have exactly 2 minutes. Asghar, do you want to comment about that?
Well, I don't know, there's little time. I had the same comment I made yesterday, that I think that the dark energy is very well known. It's a cosmological constant, nothing else. That was what I was saying yesterday, and I maintain. And of course, we do feel that we have some idea of the baryons in the dark matter halo, but we don't know very precisely how much or anything is yet. I hope that we'll be getting that. So anyhow, minor comments.
Okay. Thank you very much. Jonas, thanks again for your talk. So we can shift to the next speaker, who is Sarah Recchia. Sarah.
Okay.
Yeah, you can share your screen.
Yes.
So Sarah, we talk about the gigantic cosmic ray halos around the M31 and the Milky Ways.
Yes, thank you
Okay.
for the invitation.
Go on.
Okay, so I would like to start this discussion with a very brief review of the few things that we know about gaseous halos around the Milky Way and Andromeda galaxy. Indeed, in the last few years, there have been several observations that somehow confirmed the presence of a very extended, so 200 kiloparsec radius, hot and tenuous halo around the Milky Way. And there are information that also in Andromeda we have a similar situation. And most recently also there have been the observation of a hot bridge of gas, so a very big filament of 200 kiloparsec radius between the two galaxies. And the densities involved are at that level. So there is an important gas reservoirs around our galaxy and Andromeda that have also an important mass and could be at least a fraction of the missing baryons that we were discussing earlier. But as for our discussion, it may serve as a target for cosmic ray protons to produce gamma rays and neutrinos. And this is exactly the scenario that we are going to discuss. In fact, since Andromeda is the nearest galaxy to us, it has been observed in any possible way, and also in gamma rays. And the outcome was that the total gamma ray luminosity from this galaxy is somewhat larger than the cosmic ray content in the Milky Way. And such emission is concentrated within a region of few kiloparsec around the galactic center of this galaxy. And interestingly, it does not correlate much with the gaseous halo of the galactic disk, while in the Milky Way we have that our disk shines in gamma rays. Plus, as in the Milky Way, there has been the observation of Fermi bubbles, so these gamma ray lobes that extend for 10 kiloparsec from the disk, starting from the galactic center. Well, a similar structure probably is also present in Andromeda. So our galaxy and that galaxy are very similar. We will see also that their masses are not very different and so on. So somehow we may expect that whatever is the cosmic ray content or in general the non-thermal content of the two, they are very similar. And this can have very interesting implications because also recently Fermilab detected a very extended emission from M31 that covers basically a projected radius of 200 parsec from the center of Andromeda. And we are speaking about photons on 100 GeV, so high energies. And there have been a very thorough, let's say, analysis of this emission in which it has been considered several rings. So the inner galaxy of Andromeda, a spherical halo that extends up to 100 kiloparsec, and then an outer ring. So the conclusion of this analysis is basically that the emission from the spherical halo is very likely coming from Andromeda, while in the outer halo there is possibly a contamination with the galactic disk of our galaxy, as it can be seen from this image. And so the origin of this emission is not clear. So for the moment, we will focus on the spherical halo, but we see that so we are getting gamma rays for a very, very extending region. Consider that in typical models of galactic cosmic ray propagation, the extension of the halo is considered few kiloparsec. So here we are speaking of 100 kiloparsec. Moreover, from such analysis, it was somehow possible to extract a few informations also on the spectral shape of the emission, which is not very well constrained. In fact, while the total luminosity is quite robust as result, and we have an energy budget which is comparable to the gamma ray luminosity of the Milky Way somehow. And but for the spectral shape is not that clear. In fact, they had two different modelizations of the foreground emission of the Milky Way that gives either an exponential plus cutoff spectrum, power law plus cutoff spectrum, either a pure power law. We also will see that the implication of these two different spectral shapes are very profound, because in the pure power law situation, we may also produce neutrinos to very high energies. So, as I was saying, we have a robust indication of at least the energy budget of these gamma rays in the spherical halo. And then we may ask what is the origin of this emission. So the authors of the analysis used very rough models of galactic cosmic ray propagation and concluded that such emission cannot be really connected to cosmic rays. And they argue that it is more likely a dark matter halo origin. In our work, we did a different thing and we reconsidered the cosmic ray propagation scenario in the galaxy, and showing that if we revise it correctly, it is possible instead to accommodate such large halo and also the energetics of this emission. So when we speak about cosmic rays, basically we have two ways of producing gamma rays. Either electrons, in particular at such large distances from the disk of Andromeda, probably the dominant process is inverse Compton scattering on the CMB photons. And in this case, we would have electrons of few TeV that produce the GeV gamma rays. And in this scenario, we can also estimate the time scale of energy losses in the CMB photon field, which is very short. We are speaking about 1 million years. Consider that the residence time of cosmic rays in the lower halo of the Milky Way is larger than that values. And so, as we will see, this implies that if electrons are responsible for the emission, they must be accelerated directly in the spherical halo. While if we consider cosmic ray protons, the mechanism is proton-proton interaction. So cosmic ray protons interact with the gaseous halo that we were discussing earlier. And in this case, protons responsible for the emission will be up to 1 TeV. But the problem of proton-proton interaction is that it's not a very efficient process. Indeed, if we take the typical density of the gaseous halo, we see that we have very long time scale for production of these particles. So in order not to have to invoke very, very large cosmic ray densities in the halo, the residence time of such particles should be very long, at the order of giga-year. Just to give an idea, in the lower halo, typical values of this confinement time is below 10 to the 8 years. So this residence time should be long, but we will see that it can be accommodated. And again, I report here the typical densities of the gaseous halo. Here, for comparison, I report the cosmic ray budget of the Milky Way as observed in the disk. So we have 10 to the 41 ergs per second, and the cosmic ray density in the disk. So here we are speaking mainly about protons, which are the dominant particle, and we have an electron volt per centimeter cube. It is important to consider these numbers because when we go to the energy budget in protons needed to explain such a gamma ray halo, we see that in the halo there should be present a level of cosmic rays that in luminosity exceeds that we have in the disk of the Milky Way. While as for the cosmic ray density, it will be a bit lower, but not that much if we consider that if only a region of the spherical halo is filled by cosmic rays, this density will increase. And also if we consider smaller values than this density, we could have a density in the halo and in the disk which are comparable. And this we'll see is very difficult to account for in typical scenarios of cosmic ray propagation. So why the authors of the analysis concluded that cannot be cosmic rays? Well, basically because we have a standard model of cosmic ray propagation and origin, standard model for the cosmic ray origin, which are known to be well accelerated in sources, in particular supernova remnants, located in the galactic disk. And then they diffuse and advect out of the disk on time scale of several mega years, depending on the particle energy, up to 10 to the 7 years. And if we adopt such scenario, so production in the disk or in the galactic center, typical propagation, there is no way to populate the halo with the level that is necessary for the spherical halo of M31. Indeed, electrons cannot reach 100 kiloparsec from the disk because they are short-lived. Protons, it is problematic for one reason, basically. So the emissivity that we see will be correlated to the cosmic ray proton density and the gas density. But the cosmic ray density will decrease with the distance from the disk in any possible scenario of cosmic ray propagation, but also the gas density decreases. In fact, we have seen that while in the disk we expect 1 particle per centimeter cube, in the halo we expect 10 to minus 3, 10 to minus 4. And so if we look at this scenario, even in the most optimistic case, where we have a point source in the galactic center that injects continuously protons with a diffusion coefficient which is constant with time and with space, well, in this case, it can be shown that the cosmic ray density will decrease as 1 over r from the galactic center or from the disk, depending on what we are assuming. And then we have these densities. So if we compute the ratio that we expect in such scenario for the density of cosmic rays and the density of the gas, we should have that the disk has an emissivity at least 10 to the 5 times that of the halo, but observations of the M31 gives something which is at least a factor of 100 below. Then if we include more complicated effects such as the variations of the diffusion coefficient with space, the presence of a galactic wind, and so on, this ratio will be even larger. So if we look at typical scenarios for the cosmic ray origin, obviously it cannot work. So how can we solve this problem still using cosmic rays and not invoking a dark material origin? First of all, the obvious answer could be, well, let us accelerate particles directly in the halo. And this could be possible because, as we know from supernova remnants and from other sources in the disk, intergalactic shocks, so astrophysical shocks are very good accelerator of cosmic rays. And it could be possible to have also very large shocks in the spherical halo with a radius of 100 kiloparsec in order to justify the extension of the emission, if basically in two scenarios, either if the galaxy is accreting material, and in this case, if there is the formation of an accretion shock, particles could be accelerated there, either, as we will see, if the galactic center activity excavate bubbles in the interstellar medium, and finally this bubble grows and create a collective shock that can be also that large. So in the first case, so in the case of the accretion shock, the velocity of the shock, which is really important for accelerating particles. In fact, just to briefly summarize what happens in shocks, a fraction of the incoming energy of the flow is converted into accelerated particles, and the possibility of acceleration, the maximum energy, and the spectrum depends basically on the velocity of the shock, and especially on its Mach number. So in the case of an accretion shock, what matters is the free fall velocity, which for typical values of the total mass of the galaxies involved and of the shock radius that we are considering, it's several hundred kilometers per second. Notice the scaling with the mass, the total mass of the galaxy. This will be important for the future discussion. And from this free fall velocity, we can also estimate the luminosity so the overall luminosity energetics carried inside the shock, which is at the level of few 10 to the 42 Hertz per second. So if we consider the necessary proton and gamma ray luminosity, we see that we can accommodate it. And instead, if we consider as a source the activity of the galactic center, we still can estimate a typical velocity of the shock, which is again a few hundred kilometers per second, while the overall luminosity of this engine will be the mass of the black hole, basically the Eddington luminosity. And also in this case, it could be very easily accommodated the overall energetics. So we have seen that from the total energetics point of view, acceleration at an accretion or a termination shock, it is feasible. The other question is the maximum energy, if it can reach the energy necessary to get the 100 GeV gamma rays. And the maximum energy is basically related to the balance between the acceleration time, which depends on the shock velocity, basically on the diffusion coefficient around the shock, where A is a parameters that depends on how much the shock compresses the gas and the magnetic field around the shock. And for electrons, we need particles at least up to few TeV, and for protons up to 1 TeV. So the acceleration time for electrons will be limited by the losses. We have seen that electrons are short-lived, and if we compute this energy balance, this time balance, we get a maximum energy, which for the typical parameters is beyond what we need. So okay for electrons. We play the same game for protons, but in this case, we have seen that proton-proton interactions, so the energy loss time is very long. So what matters is the escape of particles. So the acceleration will be limited by the escape of particles from the accelerator. And if, again, we play this game, assuming that the residence time is at the order of gigayear, basically we get a maximum energy which is well beyond 1 TeV. So it could even go to very, very high energies, up to PeV. This is also very important because, as we will see, this allows for the production of high energy neutrinos. Then the spectral shape will depend basically on the Mach number of the shock, but if the shock is with Mach number above 5, and which is reasonable in this case, we will have basically a E2-2 spectrum. So this is the standard result for cosmic ray acceleration at shocks, which such spectrum is also compatible for what it is seen in gamma rays. Finally, in all these scenarios, whatever particles we are producing, an efficiency below 1% of conversion in cosmic rays is enough. So we can accommodate that. Another possibility, which does not invoke direct acceleration in the spherical halo, but a different way of transporting particles from the galactic center in the spherical halo, is based on buoyant bubbles. So this scenario is motivated by the detection of Fermi bubbles, which are likely the result of past nuclear activity in the galactic center of our galaxy, and by the fact that such structures have also been seen probably in Andromeda. So when we assume that Fermi bubbles are produced by the activity of the massive black hole, we have an energetics of 10 to the 43 Hz per second to produce such bubbles, and an energy for the single bubble of few 10 to the 27 Hz. While if it is not the galactic center itself, but the starburst activity in that region, the energetics will be different. But here we want to focus on the assumption that is the activity of the black hole that is producing these bubbles. And what happens is that, at least this is what is observed in galaxies within galaxy clusters, but recently it has also been observed in single galaxies. So the galactic center activity excavate these bubbles that then can detach from the galactic disk and start to buoyantly rise at a velocity which is roughly that of the sound speed. And in a hot ionized medium as that in the galactic halo, the sound speed is a few hundred kilometers per second. So they will rise at relatively high speed. And the survival time of these bubbles depends a lot on the structure of the bubble and on the stabilizing factors. In fact, while they rise, they increase a bit their volume, and at certain point they get disrupted by instabilities. But if the magnetic field is operating, and this has been seen in simulations, the lifetime of such bubbles can be even gigayears. And indeed, So in this view, Fermi bubbles would be just the base of a much larger structure that involve bubbles that have detached and are now in the galactic halo. So if the rate of injection of such bubbles is large enough, at the level of one bubble roughly every 10 to the 8 years, we see immediately that within 1 gigahertz we can have 10 to the 9 bubbles. And so the contribution of many bubbles can overlap in the spherical halo. And from this, taking into account a possible efficiency of conversion of the energy of this bubble in cosmic rays. Okay, also it is important to stress that observationally such bubbles have been seen to contain cosmic rays. So those are bubbles that are filled by cosmic rays. Well, it is possible to accommodate with an efficiency at the level of 10% or few the luminosity, the proton luminosity required to explain the spherical halo. Then what happens while these bubbles that typically have a radius of few kiloparsec rise in the galactic halo, at certain point, as I said, they get disrupted. At this point, cosmic rays can start to diffuse, and the way in which they fill the spherical halo depends on the diffusion coefficient. Consider that typically the diffusion coefficient is seen to increase with the particle energy. So the situation could be that below a given energy, the diffusion time is low enough that there could be the overlap of different bubbles that are rising. And in this case, we could have a sort of steady state of cosmic ray population in the galactic halo. While at large enough energy, diffusion will be so fast that the cosmic ray population become intermittent. In this case, one would observe a cutoff in the spectrum, which given the data in gamma rays could be at 100 GeV. On the other hand, if either the diffusion coefficient does not vary much in energy, either the confinement time in the halo is so long that all particles accumulate there, in this case there will be no cutoff, which is the scenario given by the second analysis of the data. So here is just a cartoon on what should happen in this scenario. So a cosmic ray inflated bubble is produced in the galactic center. It detaches at a certain point, buoyantly rise up to 100 kiloparsec. Then it gets disrupted and the cosmic rays start to diffuse, filling the spherical halo. So this is also another analogy of what happens. So the firing is done by the galactic center, and if the firing rate is large enough, we may have a very bright emission in the spherical halo, while a very intermittent and not so bright emission in the galactic center. So to summarize our results so far, we have seen that it is possible to explain with cosmic rays the emission from the spherical halo of M31, and that whatever is the scenario involved, either we have an accretion shock, and so the cosmic ray budget will scale with the mass of the galaxy, either it's related to the cosmic ray activity through a termination shock or through buoyant bubbles. In this case, the scenario scales with the black hole mass. But we have seen also that our galaxy and M31 are very similar. And in the past, there has been a very, very interesting idea put forward in 2014 that it could be possible if the residence time of cosmic rays in the halo of our galaxy is long enough to produce basically the entire flux of neutrinos, so of the diffuse neutrino flux detected by IceCube, within a region of 100 kiloparsec of our galaxy. So if we assume that this scenario is correct and we fit the neutrino flux, and from this fitting of the neutrino flux, we can infer an energy budget of cosmic rays in our galaxy. Of course, this scenario can only work in the assumption that the cosmic ray spectrum extends up to PV energies. So if the gamma rays really show a cutoff, this scenario does not work. But if the second analysis, that with a flat spectrum, works, this scenario can be effective. In fact, we have seen that it is possible to accelerate in the galactic halo protons up to PV energies. So from fitting the ice cube neutrino flux in a galactic scenario, we can infer a cosmic ray density, and then we can rescale this cosmic ray budget with the ratio of the masses and the ratio of the black hole masses between our galaxy and the M31. And from this rescaling, we can recompute the gamma ray spectrum, and we get this cyan region here. And we see that this region, this rescaled region, totally contains the gamma ray outcome of M31. So this means that there could be really a possible common origin of the ice cube neutrino flux as produced in the halo of our galaxy and the gamma rays and the gamma ray halo of M31. Given the similarities of our galaxy, this scenario is very appealing. And okay, here I clarify better the rescaling with the masses. In fact, both the total mass and the black hole mass of M31 are larger than the respective quantities of our galaxy. So in conclusion, we have seen that if a cosmic ray scenario can nicely explain the gamma ray halo of M31, and given the similarities of our two galaxies, if there is such a cosmic ray halo for M31, we could explain the gamma ray halo of M31, but also the diffuse neutrino flux of ice cube in a scenario where such neutrinos are produced in the halo of the Milky Way. So thank you for your attention.
Thank you, Sara, for your very, very interesting and clear and well done talk. Yes, really very interesting. So, any questions?
Mine is slightly, what exactly are these Fermi bubbles? What type of Fermi are we talking about?
Fermi bubbles, I will show the picture. Basically,
yeah,
gamma
Fermi
ray.
bubble.
The question is, what are Fermi bubbles, right?
What fermions?
What?
What fermions? You're saying bubbles.
The bubbles, I think, is just the gamma emissivity, gamma emission, right?
Yes, it's gamma rays. Those are gamma
so
rays.
It's photons.
Yes.
Okay.
But they are most probably produced by cosmic ray interactions, either electrons or protons, also such bubbles.
Fermi is related to the Fermi energy, not the fermion. Okay.
No, to the Fermi observatory, to the Fermi telescope.
Yeah, that's.
So Sarah, which is your favorite scenario? Is it leptonic or hadronic scenario?
So my favorite, I think, is hadronic because it's too beautiful. So you explain the gamma rays of Andromeda with a similar energy budget. You explain all the neutrinos of ice cube, so the diffuse flux at least. So the coincidence is too appealing to be tasty, let's say.
But you think there is any other way to explain this gamma emission from the M31 and our galactic halo? For example, by, I don't know, a population of millisecond pulsars distributed in the halos? Or you can say, go on.
In the sense that up to 100 kiloparsec, I don't know how many pulses. So the halo is very extended. This is the problem. So if it was just a bit larger than the galactic disk, maybe there could be pulsars or whatever, but at 100 kiloparsec, I don't know how many.
But you know that pulsars, of course, were born in the galactic disk. But when they when they born, they get generally a kick velocity with the average velocity of 600-700 kilometers per second. So in principle, there could be a population of pulsars that we don't see, but is distributed in the halo.
Okay, this I have doubts in the sense that I agree with this kick velocity. The problem is that let's imagine that they have a 200 kilometers per second. So if you compute the time to reach 50 kiloparsec or 100 kiloparsec, it is nearly 10 to the 8, 10 to the 9 years. In that time, these pulsars have run out of every possible. So if we consider the spin down luminosity, it on time scale much shorter. So it will be probably too old to do anything interesting. So really,
probably you are right. Yes.
No, but in general, I think that this is also my comment to any other. Usually, the other question is why not dark matter, in our opinion? I think that so far there is no definite evidence for saying this is not dark matter, but I would say that the energy budget is so large that my question would be if it is able to make such large energy budget in the halo, why not in the galactic center or in the galactic disk where you expect more dark matter than outside? And one would get an extremely bright disk shining in dark matter. So I don't know. I have doubts of these scenarios.
Okay, thank you again, Sarah. Any other questions? If not, we thank again Sarah and go to the next speaker. The next speaker is Lindita Molli from Tirana University. Lindita, maybe you can share your screen. Perfect.
Yes, Francesco.
So Lindita is talking about primordial black holes as dark matter candidates in the galactic halo. Please go on, Lindita.
Yes. Is it okay? Good afternoon.
Yes, yes, it's okay. It's okay. Go on.
Good afternoon. I am Lindita Molli, astrophysicist from Tirana University. This work is done in cooperation with a group of astrophysicists in Lecce University.
Lindita, sorry. Actually, I don't know if also the others, but I don't see your screen. Can you share it again?
I have shared.
Try to redo the sharing.
Yes.
Okay, now it's okay. Okay.
Okay.
Yeah.
Good.
Okay. We are focused on primordial black hole as dark matter candidates in galactic halo. Sorry. No. Primordial black holes have been recently interested recently. Their existence is proposed by Zel'dovich and Novikov in 1966 and Stephen Hawking in 1971. It is thought that primordial black holes are formed at the early universe via the collapse of the large density perturbation between the mass of the primordial black holes and the time and the formation time exists a rough relation. As can be seen, the primordial black holes span an enormous mass range from Planck mass 10 to minus 5 gram to 10 to 5 solar masses that are primordial black holes formed at 1 second after Big Bang. Primordial black holes that are formed at the present by the collapse of the source stars could never be smaller than 1 solar masses. By primordial black holes can be explained some observational conundra as lensing effects, accretion effects, dynamical effects, and gravitational wave effects. In this figure are given some constraint on primordial black holes abundance in different mass of ranges from 10 to minus 17 to 10 to 19 solar masses. It is obtained assuming a monochromatic mass function for primordial black holes. Also, primordial black holes may lead to various astrophysical consequences, providing seeds for supermassive black holes in galactic nuclei, influence the generation of the large-scale structure through Poisson fluctuations, cause important effects on the thermal and ionization history of the universe, and the most exciting possibility is that could provide a non-negligible fraction of the dark matter. The primordial black holes with original mass lower than 10 to 15 grams would not have survived to the present due to the Hawking radiation. So attention have to shift it to primordial black holes with larger mass. The goal of this work is to investigate the traces of the primordial black holes in galactic halo. Since they do not emit the light, the gravitational microlensing is the best method to detect them. We have selected 4 targets: galactic bulge, large and small Magellanic clouds, and M31. In this direction, we have calculated the optical depth, microlensing rate, and microlensing timescale. Also, based on the capability of Euclid telescope, we discuss about the constraint on primordial black holes abundance. Here are given some theory and geometry about gravitational lensing. A light ray from a distant source, when passes close to the lens, it is bent with an angle alpha, which is calculated by this formula. Between the angular position of the source images theta and the angular position of the source beta, there exists this relation, which is called lens equations. Here, theta e is the Einstein angular radius, which is it is calculated by this formula. It depends by the mass of the lens and the distance, observer lens, observer source, and lens source. There are 3 classes of the strong of the gravitational lensing: strong lensing, weak lensing, and micro lensing. We are focused on micro lensing. In this case, the separation between images is the order of the micro arc seconds, so they cannot be resolved. During a micro lensing event, when an object passes close to the line of sight toward distant source, what can be observed is the brightness of the source stars, which is increased up to maximum value and then decrease. Here is given a plot of the amplification of the source star by the times. In the case when observer, lens and source are perfectly aligned, the image of the source is a ring, which is called Einstein ring. Here are shown some gravitational microlensing curve Their amplification is calculated by this formula, where U is the distance between the source position projected to the lens plane with the lens in units of the Einstein radius, when source during its trajectory is on the Einstein ring, the dashed line. The value of the U is equals 1. At this moment, the threshold amplification is 1.34. From microlensing events can be defined 3 parameters. U0, which is the impact parameter, the smallest distance between the source and the lens. It is related to the maximum of the curve. T0, which is the time of the maximum, and Einstein time. Among these, only Einstein time obtain information about the lens. So only by this cannot be defined the parameter of the lens. This is called parameter degeneracy. To break this, have to be considered the second order effects as parallax effects and finite source effects. The Einstein time is given by the ratio of the Einstein radius to transit velocity, where Einstein radius is calculated by this formula. In fact, gravitational microlensing is an unpredictable event, and optical depth define the probability that any given star is lensed at any given time by a foreground compact object. For a star and for a model of the lens density distribution, the optical depth is calculated by this formula, where n is the number density of the lens. It is given by this ratio, since the RE squared is proportional to the m. The optical depth does not depend on the mass of the lens. It is proportional to UT in squared. Here is shown a figure of microlensing tube. A microlensing event happens when object go through it. Another quantity that we calculate is the microlensing rate. It is the rate at which a given background star undergoes a microlensing event due to a foreground lensing object. It is calculated by this integration, where n is the number density of the lens, fv is the velocity distribution, this is the volume element, velocity element. They are calculated assuming a cylindrical coordinate along the line of sign, assuming Maxwellian velocity distribution and including some parameters. The final formula by which we calculate the rate for a star at distance ds is given by this. It is proportional to UT and is dependent by the mass of the lens. It is proportional to 1 over square root of m. And here in this figure are shown the galactic halo. We have assumed that it composed by the primordial black holes, and are shown 4 targets that we consider: galactic bunch, LMC, SMC, and M31. These are their distance and galactic coordinate. Concerning the dark matter in the Milky Way halo, we assume a standard halo model with dark matter density given by this relation. These are the value of the parameters. Considering a scenario in which primordial black holes constitute the fraction f of the dark matter, the mass density of the primordial black holes is equals to f times density mass of the dark matter. Related to the stars in the bulge, we have assumed a triaxial bulge model with mass density given by this relation, and here are the value of the parameters. With the star in the LMC, we have considered a distribution as luminous, disk, and bar. These are mass density distribution together with the value of the parameters. For stars in SMC, we have considered two populations of the stars, old stars and young star population. These are mass density distribution. Here we have to emphasize that the center of the young star population is a distance of 2 kiloparsec behind of the old star population. And the star in Milky Way, and the star M31, since it has the same morphology with Milky Way, we have assumed distribution as a bulge on the disk. Here are their mass density and the value of the parameters. And now result about the optical depth, since the sources are not of the same distance, but they are distributed along the line of sight from minimal distance to maximal. We calculate the average optical depth by this formula. For a value f equals to 1 and ut equals to 1, we find this value, which are shown in this table. As can see, the largest value are taken in the case of M31 and the smallest for Milky Way bulge. Also, we remark that the optical depth towards SMC is larger than LMC with a factor of 1.4. Also, concerning the SMC, we see the visible difference between the contribution of the two population stars, mainly due to the fact that their center is shifted with a distance 2 kiloparsec with respect to the other. And now result about microlensing rate, since it depends by the mass of the lens. We have considered a range from 10 to minus 14 to 10 to 2 solar masses. Also, we have assumed a monochromatic mass function. For f equals to 1 and ut equals 1, and for this value of the velocity of dispersion, velocity dispersion, we take this value, which are shown in this figure. These are the gravitational rate per year per star. They vary from 10 to minus 7 for upper limit of the range to 10 for lower limit in the range. So the larger value are taken in the case of M31. And now, since the microlensing time scale, TE, is related to the optical depth and microlensing rate by this relation, in this table we have shown the value of time scale for two limits of the mass range. As can see, the value of time scale change of several order of magnitude from a fraction of seconds up to several years. And now some conclusion about Euclid observation. It is a medium of class mission of European Space Agency. It is scheduled to be launched in 2022. In fact, has planned for weak lensing observation, but additional survey towards galactic bulge for a few months is possible. These are galactic coordinate of Euclid observation towards the galactic bulge. In this direction, we take this value for optical depth and for microlensing rate. Concerning assuming magnitude limit 24 and mass luminosity relation, we find that the minimum mass of the source star that can be detected by the Euclid is 0.31 solar masses. Also, based on the salpeter mass function for the stars in the bulge, we find their mean mass value, which is 0.97 solar masses. Considering for the source in bulge at a distance from 7 to 10 kiloparsec, and assuming a mass density distribution given above on the field of Euclid, on the field of view of the Euclid 0.54 square degree, we find that the number of source stars that can be observed by Euclid is given by this value. By multiplying microlensing rate, number of solar stars and the time of observation, we find that Euclid will observe 314 microlensing events per year, with the time scale about 8 months in the case when primordial black holes has a mass as solar masses. These results are taken for F equals to 1 and UT equals to 6.54. The last one is obtained by considering the photometric error for Euclid telescope 0.1%. In this figure are shown our result for microlensing rate per star per year, black line, and microlensing time scale, blue line, for different value of the mass of the primordial black holes, considering a cadence of 20 minutes and no less than 5 points within time scales. We find that Euclid will observe primordial black holes with mass down to 10 to minus 7 solar masses. And here our conclusion. We estimate the optical depth and rate towards 4 targets: galactic bulge, LMC, SMC, and M31. We have assumed that galactic halo is composed by primordial black holes with a monochromatic mass function distribution. We find that the largest value are found for observation towards M31 galaxy. It is due to its larger distance. For this mass of range, for primordial black holes, the time scale changes by several orders of magnitude. So different observation strategies are needed in order to detect primordial black holes in different beams of mass. Also related to the Euclid result, we find that it will observe 340 events per year, with a time scale about 8 months for primordial black holes with mass as solar masses. So we find that the minimal mass of the primordial black holes that can be detected by the Euclid is 10 to minus 7 solar masses. So around this value, we estimate that Euclid will observe this number of microlensing events. In our analysis, we have not considered self-lensing events and contribution from the primordial black holes in the halo of SMC, LMC, and M31. Thank you for your attention. And any question?
Thank you very much, Lindita, for your nice presentation. So we have a few minutes for questions. Does anyone want to ask anything to Lindita?
Yeah.
Asper?
Yeah, excuse me.
Yeah.
Should I switch on video?
Ashray, right?
Yes, Harshraj.
Okay, please go on.
So I have a question regarding the beginning, as in the basic assumption that the primordial black holes could be the dark matter content of the galaxy. As in, just on the basis of mass, are we assuming that a big enough, say around 10,000 or 100,000 primordial black holes combined to form the galactic halo? That's something like I have an issue with.
I don't hear.
Okay, so the mass of a primordial black hole would be around 10 to the power 7 solar masses, right?
No, I think, Linda, maybe you can show the mass range of the primordial black holes, you assume.
The mass range of the primordial black hole are...
Okay. 10 to the power 2. Oh, sorry. Okay, so even then, if the primordial black holes have masses in this range, this is even smaller than, like, there's a difference of 10 to the power 10 in the order of magnitude when it comes to the mass of the galactic halo, the dark matter halo. Like, I'm just talking about the Milky Way galaxy. So the mass of the Milky Way galaxy is 10 to the power 12 solar masses in that order. So how are we, like, are we assuming that the individual primordial black holes, like about 10 to the power 10 of them combined to form the halo?
I also don't follow exactly your question.
I don't hear very well.
Can I just comment that maybe what is being considered by the questioner is as if the entire halo is composed of primordial black holes. This is not what was being taken here. It's that primordial black holes could contribute to the halo. Not that it has to be all made up of the primordial.
Yeah, sure.
That I think was a confusion.
They contribute for a fraction of the, which is a free parameter from 0 to 1.
Okay. Sorry about
that. Any other questions? Yeah, sure.
Thank you. I'm Stefano Bondani from University of Sofia. It's just a curiosity. You have assumed a monochromatic mass function. Do you have any idea of how your results might be modified by assuming a non-monochromatic mass function? Let's say, for example, a log normal, or if you know of anyone that has done such a work and you can point me to it. Thank you.
Lindita, did you follow the question? Do you know?
Can I just ask Dr. Harshad to put his hand down now? It's still up.
Oh yes, Harshad. Yeah. Thank you. So Lindita, you have assumed a delta function for the mass distribution of the primordial black hole. The question is if you have investigated what could happen if you change this assumption.
In this, our result, we have considered only monochromatic mass function. All primordial black holes have the same mass, and it assumes that it comprises a fraction f of the galactic halo.
Yes, thank you. I was in fact wondering if you had any idea of how your work, your results might be modified by assuming a non-monochromatic mass function.
Yes, I think the question is interesting and should be a next step to investigate.
And if you know of anyone that has done that kind of work, I would be very much interested to read.
Okay, good. Okay.
Thank you.
Yes, there is a paper submitted about that. Okay, thank you.
Stop. I have.
Sorry. Any other questions?
Oh.
Okay, if not, let's move to the next speaker with Antonio Franco.
Oh.
Okay, I'm sharing the screen.
Yes. Antonio is started his PhD just a few months ago, and he will present some very, very preliminary results about searching for intermediate mass black holes in the Milky Way's galactic halo.
Okay, can you see the screen?
You can go on. Yes, we see your screen.
Okay. Thank you so much. I'm Antonio Franco. I'm a PhD student at the University of Lecce in Italy. And today I'm going to present some preliminary results about how it's possible to detect intermediate mass black holes in the Milky Way's galactic halo. But just a quick review, theoretical and historical review. The first idea about black hole was provided by the first time by Mitchell and Laplace during the last year of 18th centuries when they thought about the existence of dark stars. But the first formalization was given by the Schwarzschild solution of the Einstein field equations in the 1916. But the name black hole was provided by Wheeler just a few years later in 1967. We know there are three main classes of black holes. Stellar mass black holes with a mass up to about 30 solar masses, which are formed by the gravitational collapse at the end of the life of more high massive stars, so stars with a mass about of 20 solar masses. And we can detect this object, for example, when they are in a binary system, so with the electromagnetic emission due to the accretion process, or with gravitational processes like gravitational lensing or gravitational waves. There are also supermassive black holes with a mass between 10 to the 6 and 10 to the 10 solar masses that are at the center of almost each galaxy in the universe. And we can see this object indirectly, for example, when they are with the gravitational perturbation of these objects to nearby stars, or with imaging of the accretion disk, like for the M87 case, or with the electromagnetic emission in the same way. But we have also a middle class of black holes that are the intermediate mass black holes between 30 and 10 to the 6 solar masses. And actually, we didn't expect these black holes simply for these the range of masses. But there are some evidences about their existence. For example, thanks to LIGO-Virgo collaboration, that detected some binary systems that with merging formed intermediate mass black hole. So it's possible to so that these black holes may provide the part of the contribution of the galactic halos dark matter, but actually we don't know about their real distribution in the galaxies. So there are some possible mechanisms for their formation, for example, from population 3 stars or by gravitational runaway. So when low massive black holes collide and form an intermediate mass black hole, or when we have dense star clusters and the stars collide and produce a huge stars that directly collapse into intermediate mass black holes, or via a primordial process. And this last idea was first suggested by Zel'dovich and Hawking when they thought about the possibility to have a black hole during the first stage of the universe, where
the high density and heterogeneous condition of the universe were enough to produce a local gravitational collapse and then a black hole. And in this way, it's possible to obtain any kind of black hole, from stellar mass black holes to supermassive black holes. The mass of the primordial black holes is related to the production time, and if we consider the formation before the electron wave phase transition, we have a mass less than 10⁻⁷ solar masses, but in principle, we can have also more massive black holes. Considering the Hawking radiation, the evaporation time is related to the Cabi power of the mass of the black hole. And if we want to consider just not evaporated black hole, we have to consider this mass of range between 10⁻⁸ and 10⁻⁷ solar masses. That is the mass produced, obtained with the standard Kerr Hawking mechanism. But if we consider a different mechanism based on parametric resonance and hybrid inflation, we have mass of a range between 10⁻⁸ and 10⁻⁷. And in this range, it's possible to define a smaller range between about 10⁻², we can say, and 10⁶ solar masses. That is the typical range for intermediate mass black holes. So we can say that intermediate mass black hole can be formed also in the very early universe. There are many techniques to observe black holes in general, and one of these is the gravitational lensing. This phenomenon shows up when an object, that is a lens, stands in the way between the observer and the source. And the gravitational field of the lens deflects the radiation coming from the source, and in this way the observer can see more virtual images of the source. But if it's not possible to resolve, to separate these virtual images, we can see just an amplification of radiation of the source. And this amplification follows the Paczynski law that is related to the U parameter, that is the angular separation between the lens and the source in Einstein's angular unit. But now we talk about our idea. In fact, for the detection of intermediate mass black holes, we used the dark energy camera, that is an instrument installed on the focal plane of the Victor Blanco telescope at the Cerro Tollo Inter-American Observatory in Chile. It is composed of a grid of 62 CCDs, which cover a field of view of about 3 square degrees, using the GRI-ZY filters that are the same filters used in the Solar Digital Sky Survey. Well, our idea is to intensively observe the Magellanic Clouds for the possible detection of massive compact halo objects via macrolensing. And if we consider the typical macrolensing rate toward LMC, that is proportional to 10⁻⁶ events per year, we expect about 50 macrolensing events over 2 years of data, with an expected mass up to 300 solar masses, so also intermediate mass black holes. Here we can see on the left the different acquisition of the DCAM instrument, that are these green dots, and in particular toward LMC and SMC. On the right, on the upright, we can see the typical field of view toward LMC, and on the bottom there is one of the DCAM field, that is the F1538801 field. And for this preliminary work, we used 36 images in the G band acquired between 2019 and 2020. We also used ICES 2.2 subtraction package provided by Allard, and this is a very useful software for the detection of variable sources. Particularly, this software makes an interpolation between the images, providing an alignment, creates a reference image, and uses this image for the subtraction. So it makes a subtraction between each image of the sample and this reference image. So in this way, it's possible to highlight the brightness difference for the variable sources. So it's possible to detect the variable sources and carry out the photometry. We also use the Czerny algorithm to have the phase light curve and the period for the periodic sources. Here we show our one microlensing candidate. This is the position in the sky of this event, and on the right we can see the differential luminosity over time for this candidate, and we can see that the luminosity increase over time, and we can see this luminosity also in the light curve, where here there are our data, the red dots, and on the white we can see the Paczynski law. But it's important to know that this is not best fit. So this is just a preliminary fit, so we have to do further analysis, but we wanted just to understand if our data followed the theoretical curve. And we report here what the Einstein time, that seems to be about 150 days. We also detected other variable sources, like for example, periodic variables. And actually, we used known variables to test our pipeline. And here we have an eclipsing binary, an error Lyry, and 2 classical C-fades. And we can estimate the period with the Czerny algorithm, that is this PDAT, and the PCAT, that is the cataloged period. And we can see that these 2 periods are very close. So our procedure is very, very good. We also detected new variable sources, and we detect about from 5 to 10 new variables per single CCD. In this case, we have a long period variable candidate, but there is no periodicity, so we don't know what actually this variable is. Maybe an AGN, a quasar, or long macrolensing event, we don't know. And here there are 2 eclipsing binary candidates where we can estimate the period of these 2 sources. So to conclude, in this way, in this work, we can confirm the goodness of our pipeline for detection of variable sources, both periodic and non-periodic. And for the last one, it's possible to, we confirm the possibility to detect macrolensing events, also due to intermediate mass black holes. And until now, we detected about 2,000 known variables toward LMC and about 1,000 unknown variables. But for these variables, their real nature must be proved in the next future. So that's all, and thank you so much.
Okay, thanks, Antonio, for your nice presentation. Any questions? Oh. One question.
If nobody
yes.
else has a question, of course, we have seen intermediate black holes being produced, intermediate mass black holes. When 2 black holes merge, they may go over 30 solar masses. So
Yes.
they are there.
You mean from the gravitational wave events?
Yeah.
Yeah,
With the merging of black holes.
How many there are, and of course, one could start getting vague estimates by looking at the number of mergers that we have seen in this much time. How much have we seen? So how much should there be around up to now in all? That may give a rough, very rough estimate. And that much should be there in any case. So perhaps one needs to also just look at that aspect.
Yeah, you mean
just a number of black holes that we could observe? Because the number of black holes toward LMC is about, of course, it's just statistical number, but is slides is about 20. Of course, this is not a number of primordial black holes. This is just a number for macrolensing event that we expect to observe toward LMC.
Yes, that's what you said. Is this expectation on the basis of what we have seen?
No. This is not correlated to primordial black holes.
That's what I thought. My point was that maybe it's a good idea to connect it with what one has actually seen. How much of this would come from there?
Oh well,
What we've seen is
we
much.
didn't study
We've seen
these.
some.
We didn't study these correlation actually. It will be very useful to study, but this work was focusing on the detection of microlensing events in general, also due to primordial black holes, but I can't say now a correlation.
I think that one can investigate towards
Yes,
the
yes,
direction
course.
suggested by Professor Kadir. Yes, it's a good
Yes.
idea. Okay, thanks again, Antonio.
Thank you.
If there is no other question, let's go to the next speaker, Knowledge Tire. Knowledge, can you share your screen? Knowledge will talk about virial clouds evolution from the surface of the scattering up to the formation of population tree stars. Yes, we can see your screen. Okay, you can go on, please.
I'm Naresh Thayer and I'm a PhD student at the University of Zel'dovich. So today I'm talking about the evolution of clouds. Yes, sir.
I can't hear Maurice.
Now can you hear me?
Yeah, now.
Okay. So we all know that there is evidences that we have more matter outside the core of the galaxies than we can see in the galactic disks. And this matter is more or less known as dark matter. So if we want to fit this matter with the observation, we have to go out of the disks up to like 10 times the radius of the core. So like greater than 15 kiloparsecs or 10 kiloparsecs, we should go search for this matter outside the core. This part of the galaxies where we are looking for dark matter is known as galactic halos, or normally we call them dark halos. So it is well known from the standard cosmological model that the universe is made up of 5% baryonic dark matter. So the 5% of observable universe is baryonic dark matter. 60% of these baryons are detected in the luminous parts of the galaxies in the form of the warm hot intergalactic gas, and in the form of CGM, in the form of ICM, the intercluster medium, and some in the form of cold gas. But what leaves behind is the 40%. This 40% percent of baryons are still undetected, and we call it the so-called missing baryon problem. So one could expect that all these baryons are in the form of hot intergalactic medium like winds. So we can expect that these baryons might be present in hot gas around the galactic halos, inside the galactic halos, around the disks. But it is not possible because some of these baryons should reside in the galactic halos, and there is evidence that a non-negligible fraction of baryons are in the galactic halos. But we do not know how much fraction of these baryons are in the halos. So we need to expect some fraction, and we need to investigate this fraction and estimate the fraction by using some models. So one of the proposal was there are pure molecular hydrogen clouds in the galactic halos, and these clouds are at exactly the CMB temperature. So they are merged with the CMB, and they contribute to the galactic halo dark matter. So a suggestion to look for these kind of chameleon clouds was to look for an asymmetric Doppler effect in the CMB due to the rotation of these clouds. So the suggestion was to look towards M31, and the part of M31 rotating towards us should be blue shifted, and the other part rotating away from us should be red shifted. Then there came the Planck data. So the Planck data was a window to observe the clouds. The data was analyzed, and there was a temperature asymmetry that was observed towards M31 disk. Not only for M31 disk, it was seen for like M31 halo as well. The asymmetry, the observed asymmetry was detected at about 100 kiloparsecs. And it was also seen that this asymmetry, this temperature asymmetry, was almost frequency independent. So this was a strong indication that there is a Doppler shift due to the halo rotation. Not only for M31, it was seen for 5 other galaxies, including Centaurus A, M82, M33, M81, and recently for Sombrero. So the fact that the temperature asymmetry was almost frequency independent, and it supported a strong indication for the presence of some clouds in the halos, and but the problem was this asymmetry was not telling that what kind of clouds are these, i.e. For example, these clouds, what kind of molecules or atoms these clouds might contain. These are not pure molecular hydrogen clouds, it was sure. There was helium, there was dust in the galactic halos that could contaminate the clouds. So how much the contamination is in the clouds how much contamination of dust and helium is in the clouds, and how much this contamination is affecting the physical parameters of the cloud was needed to estimate. So since the clouds were at variable temperature, so we called them variable clouds. And then keeping the things in mind, the conditions for the formation of the cloud and the temperature, we modeled the clouds and estimated the mass, radius, and densities of the clouds at the current CMB temperature. But observing the Doppler shift due to galactic halo rotation and modeling the variable clouds at the current CMB temperature does not explain the true nature of these clouds. In order to see the true nature of these clouds and to confront them with the observational data, i.e. The observed rotational asymmetry and other kind of astrophysical data, we need to see the evolution of these clouds. We need to estimate the true nature, the true concentration of molecules, the exact mass, and the radius and the density distribution of the cloud. So our task was divided into 2 steps. The first step was to look at the evolution of the clouds from the surface of last scattering, since the clouds were formed at the surface of last scattering when the universe was very hot. And we extended the evolution one up to the formation of population 3 star, because it was not very tricky to do this before the population of 3 star. The tricky thing comes in evolution 2, when the population 3 stars formed and to the present. So evolution 2 is to be studied in the next steps, and for the moment I'm discussing evolution 1. So we know that there should be variable clouds formed at the surface of last scattering when the redshift was about 1100 and the CMB temperature was about 3000 kelvins. At that time, the universe contained primordial fraction of atomic hydrogen and helium, which is 75% atomic hydrogen and 25% helium by mass. One could question that there are other kinds of molecules and atoms. Yes, there were other kinds of atoms like deuterium, helium-3, lithium, and molecular hydrogen. But the ratio of these molecules and atoms were very negligible. So we assume that we just neglected these atoms because their fraction was sufficiently very negligible, and there were no sufficient contribution in the evolution 1 of the variable clouds. Now we modeled the clouds. The clouds were in thermal equilibrium with the CMB. So they are in a heat bath, which is CMB, and they should remain thermalized with the CMB if we want them to remain stable. If they are not stable, they should collapse to form some astrophysical object like a planet or a star. So we have to use the canonical ensemble distribution. This is just a statistics. For a fixed temperature, and we need to use the cooling of the heat path to provide a quasi-equilibrium. So we need to decrease the temperature, like the decrease in temperature of the CMB, and see how the mass and density is varied. Another thing was the clouds should form in a potential well of the cold dark matter, since the universe was in a dark age, and there it was the dominated cold dark matter potential, which was allowing the atoms and molecules to collapse. So it should remain in a potential well of cold dark matter. But the good thing for virial clouds was they were thermalized. So if they are thermalized, the potential well will not cause them to collapse. If they collapse, they will form population 3 stars. If they don't collapse, they will form virial clouds. So there are virial clouds, and there are such clouds which are forming population 3 stars. For the moment, for generality, we consider a virial cloud, let's say, composed up of arbitrary mixture of hydrogen and helium, with a mass fraction of alpha and beta. Alpha is the fraction of atomic hydrogen, and beta is the fraction of helium, which is going to be fixed afterwards. So then we use the cosmological fractions of H and He for the final computation. So the total mass of the cloud will be like the mass of hydrogen, atomic hydrogen, the total mass of atomic hydrogen multiplied by the fraction of atomic hydrogen plus the fraction of helium multiplied by the total mass of helium within R. And the condition are this alpha plus beta should be equals to 1. So the density distribution, since the cloud is a two fluid cloud which contains only hydrogen and helium, the density distribution should be of the form this, where zeta is a factor which depends upon the temperature and the densities of atomic hydrogen and helium, and the mass of single atom of hydrogen and the mass of single atom of helium. G is just the Newton's gravitational constant. So the corresponding with the we estimated the differential equation using equation 1, and which comes out like this. We need to solve the differential equation to estimate the density profile. So and tau is given by this factor. Tau is a constant factor here. We solve equation 2, the differential equation. The differential equation was solved numerically. For the moment, with a gas value of a central density, we made an arbitrary value of central density, and and modeled the distribution of the cloud at this temperature, and saw that if the gene's radius, if the density was getting exactly 0 at the gene's radius, because the boundary condition were at R is equals to 0, the density was approximately the central density. But at R is equals to the gene's radius, where the cloud has a fixed boundary, because the cloud has a fixed boundary, there should be the density going to 0. So if it was, we used arbitrary central density, and then we checked that if the density is exactly 0 at the border, if it was not exactly 0 at the border, we increased or decreased the central density, and checked that at the gene's radius, the cloud radius or the gene's radius, the density was getting 0, and we estimated the density profile. For each temperature, we estimated the central density. Like we varied the temperature from 3000 to I think it was from 1100 to 50. The redshift was changing, so we estimated at each redshift, at each temperature, the central density, and estimated the variation in the central density. The same goes with the mass. We have the density, we have the radius, we integrated the density over the whole volume. So we estimated the total mass of the cloud. So the mass was a cloud was about of the order of 10 to the 5 solar masses, and it was decreasing with the decrease in temperature, but the central density was increasing with the decrease in the temperature, and the change in central density was very fast during the earlier evolution, and then it becomes slow during the later evolution. And the variation in genes mass was very was not very slow, but it was slow as compared to the later evolution. So the cloud should lose mass frequently in later times than in the beginning. and also the radius. The radius was decreasing with the increase in temperature. There was a frequent decrease in radius, and then it should go like very slow in the end. So we have seen the evolution of these clouds from the surface of last scattering up to the formation of population 3 stars. This was precisely determinable. Since we were dealing with an era of about z equals to 1100 to z equals to 50, one might expect that there will be a gravitational clamping in the dark matter gravitation. Well, where there will be gravitational binding energy and hence cooling, so that molecular hydrogen would be more likely to form. There should be molecular hydrogen, and after this, more frequently forming. But during this era, there was less molecular hydrogen, and it was not stable because hydrogen, the molecular hydrogen component will be negligible in any case. So because there was no dust grains, the formed molecular hydrogen could be destroyed because of the radiation pressure and anything else. So we do not need to include the cooling from molecular hydrogen until and unless population 3 stars exploded and there was dust coming in to form molecular hydrogen. Now our next step is to see how these how these various clouds would evolve after the explosion of population 3 stars. Since the explosion of population 3 stars, no other fluids or substantial contaminants should be present in the various clouds. I.e., there was no dust in the clouds. There will be only hydrogen and helium, and no heavier molecules with more frequent fraction. However, for the subsequent steps of the cloud evolution, we would need to include more fluids, like we need to introduce more heavier atoms and dust grains after the explosion of population 3 stars in the ISM. There would be something that is changing, like there should be more modes coming in, like vibrations or rotations, and there should be more quantum effects coming in. So these dust grains should have an important role in the cloud evolution, since they would act as catalyst to form, and also they would act as a catalyst for molecular hydrogen. So there should be more frequent cooling processes coming in. All these things will be considered in the evolution 2 of the variable clouds. So that's it. Thanks so much. If there are any questions.
Okay, Nora, thanks for your talk. Any questions or comments? Can you share meanwhile your screen?
I have a question. This is Jonas Chavez. So what is the fraction of the total amount of baryons that you expect to be in this type of clouds?
For the moment, we assume that we didn't. For the moment, we assume that all the baryons are in the clouds. We have not changed the fraction. Like we have considered that all the baryons are in the clouds for the moment, but we can change. We need to check it.
No.
We need to check.
Sorry, I mean of the total amount of baryons in the universe. So you know that there is around 10% of baryons, well, or 7% of baryons in galaxies. So what will be the fraction of all the baryons here?
There should be so I don't know, maybe for the baryons we assume that all the missing baryons are in the clouds, not typical fraction. All the missing baryons. For the moment we assume that all the missing baryons are in the cloud, but we need to see how much, because we are modeling, and after the modeling we can see how much baryons should be present.
Perhaps I can clarify one point that we're not at the moment in a position to say what fraction of the matter is in the cloud. We know that they're there because of the asymmetric frequency shift, the antisymmetric frequency shift. But we don't know how much that is. We have no way of saying there are so many clouds with so much mass in all. Yet we haven't got that. When he was talking about confronting the data, that's exactly what we need to be able to do, for which we need the modeling to be done more precisely, and then we should be able to get that.
Okay. Any other questions? Okay, if not, we can move to the last speaker, who is Muhammad Bilal, or Bilal, from the Abdul Salam School of Mathematics.
Yes.
Muhammad, can you share your screen meanwhile? Muhammad will talk about the analysis of the velocity rotational curves via violent interaction modified gravity. Yes, we can see your screen now.
Can you see my screen?
Yes.
Yep. Our
Okay.
topic is analysis of the velocity rotational curves via violent interaction modified gravity. Our plan of the talk is observation.
Can you go to the full screen? Bilal, can you go to the full screen? This is
yes,
the...
Okay.
You should press F11
Okay.
Okay.
or try to scroll up.
I think it's okay. We can see, I can see clearly your screen.
Okay, now I will start off my topic. Our plan of the talk is observational status of the general relativity to explain cosmology. Now, after we discuss modified Newtonian dynamics and the modification of the gravitational Lagrangian area, and the last next is modified electricity dynamics, and the last is the nature of the galactic halos of M31 all of we know in 1915 Einstein's theory of relativity came to light This should revolutionize our understanding about the concept of gravity. Gravity is nothing but the curvature of the space-time. This is the famous Einstein question for general relativity. Now we discuss tests of the general relativity observational status. The preliminary experiments of general relativity gave results that were discernibly measured by the technology of the day. According to the Newtonian theory, the Pellian shift of Mercury is 543 R per second per century, but according to astronomical observation, it is 43 per hour per century, which general relativity explains very best. Now, Einstein next observation is the in 1959 after Einstein's death. Now, Einstein theory, and when Einstein applied his theory of relativity to cosmology, he considered that the universe was static. But in 1922, Friedman proposed his model about the structure of universe. In his model, the universe was not static, but it is time dependent. Either in Friedman equation, if we consider there are scale factor equal to 0, in Friedman equation, the spatial coordinates are fixed and the distance rho by a scale factor AT which shows you the universe is expanding or contracting. If we consider the scale factor equal to 0 if we consider scale factor equal to 0, then 8 pi g over 3 equal to kappa over a squared. For k equal to 1, for k equal to positive 1, the density should be greater than 0 and pressure must be negative. So in Friedman model, there is no possibility of the static universe. After 1920, some limit draft result which shows that the distance galaxy could be redshift and their speed would be proportional to their distances. In 1929, Hubble also observed the redshift of galaxies and gave a law. According to the Hubble law, the universe is not static, but there's a correlation between distance and velocity. Where h naught is an Hubble constant, Hubble constant, the current measurement of Hubble constant is 70 km per second per megaparsec. Now we come to the density parameter and the dark matter. The density parameter is a ratio of the average density of the matter and energy in the universe to the critical density. The critical density, the density at which the universe would stop expanding only after an infinite time. Now the density parameter would determine the future of the universe. density, the universe will stop its expansion after a finite time. If rho equal to rho c, the universe is asymptotically flat. According to the current research आ गया और standard cosmological model, omega not near equal to 1 आ गया. Omega not equal to omega BR plus omega DM plus omega BR is a normal baryonic matter density parameter. Omega DM is a dark matter density parameter, and omega is a dark energy density parameter. This omega naught will determine the future of the universe आ गया. If omega naught greater than 1, then universe would be closed. If omega naught equal to 1, the universe will be flat. If omega naught less than 1, the universe would be open. But standard cosmological model favored omega naught equal to 1, means the universe will asymptotically flat. Now in 1975, American astronomer Robin published a paper on the galaxy rotation galaxies. She
Muhammad, from time to time we miss your voice.
matter as a dark matter arc. Due to the existence of the dark matter, the velocity rotation curve will not fall off but remain relatively constant. Now we discuss dark matter and its evidences are. Observation experiments predicted that 23% matter of the universe is not shining, neither interact with electromagnetic radiation nor with ordinary matter called dark matter, and violated the nucleosynthesis constraints. Data necessary for the baryonic dark matter. No first evidence of the existence of dark matter is the galactic cluster mass. The mass of the galactic cluster calculated by virial theorem showed that there is much more matter than the luminous matter. For example, the mass of the Coma cluster lies at a distance of 100 megaparsec in the constellation of Coma Berenices shows that there is a much more matter in the Coma cluster than the luminous matter. The next evidence is gravitational lensing. Presence of the massive object curve, the geometry of the spacetime and bending of spacetime alter the path of the light. The gravitational lens magnifies and distorts the distant objects because dark matter effects are detectable via gravity and provide evidence for the existence of the dark matter. For the gravitational lensing, 90% matter of the 90% dark matter contributed in the effect of the gravitational lensing, while 10% baryonic matter contribute in the effect of the gravitational lensing. The next is the cluster of the galaxies with hot gas. The next evidence is cluster of the galaxies with hot gas. To trap the presence of a hot gas and visible X-phase gas is a sign of the existence of dark matter in the cluster of galaxies. To trap a gas or to observe it in the cluster of a galaxy, large amount of matter is required than the visible matter. Observation of the Coma cluster by the X-ray sprite shows that there is much more matter in the Coma cluster that is required to trap the X-rays in the Coma cluster. Now we come to the different models that were used to describe the nature of the dark matter. The first is the standard model of particle physics. Standard model of particle physics is a framework that describes all non-elementary particles and explain the four of the non-fundamental forces of nature. The major problem of the cosmology is that in standard model of particles, we do not find any particle that provides us information about the nature of the dark matter. In standard model of particles, we have 6 quarks and 6 leptons and 3 interaction forces. The W and Z boson, the W and Z boson participates for the weak interaction force, gamma rays for the electromagnetism, and gluon for the strong nuclear force. While Higgs boson was discovered in 2013, data participated in the Higgs field. In standard model of particle physics, standard model of particle physics do not provide any information about the nature of the dark matter. The next theory was proposed is the supersymmetry theory. In supersymmetry theory is the extension of the standard model of particle physics. In supersymmetry theory, every fundamental boson has a fermions. However, the experiment performed a large hadron collider to observe the supersymmetric particle of the electron, which is electron, has failed. Supersymmetry theory does not provide us any information about the nature of the dark matter because we did not find any particle, any supersymmetric particle of the electron in a large hadron collider at a sufficient temperature. The next way to explain the dark matter problem is the modified Newtonian dynamics, which was proposed by Milgram and Israeli physicists. One suggestion for a dark matter problem had been to modify the existing theory of gravity. One of the proposals was a modified theory of gravity, was modified Newtonian dynamics, but it had a serious drawbacks. It was non-relativistic and it did not provide unified fitting for all scale. It provides fitting for one galaxy, but when come to the cluster of galaxies, it does not provide unified fitting for the rotational velocity curve. Next attempt, but next we could the top now gravitational Lagrangian and its modification. After one attempts were made with FRT theory of gravity, where H scalar and T is a torsion tensor. Those are torsion tensor. But in this, there is many new parameters created that do not provide any information about the velocity rotation curves of the dark matter. Later on, Hardcore suggested that modified gravity should be used. Recently, a new novel explanation for to explain the dark matter theory has been emerged. One of the such proposal was modified relativistic dynamics. Kadir, Lee, and Kim had proposed the modification of the Einstein-Hilbert Lagrangian with cosmological constant by adding a product of the Riches and the matter tensor, Riches scalar and the matter tensor. Now in 2019, the Kadir and Lee proposed coupling the matter with a Weyl curvature. Actually, we are taking the gravitational Lagrangian that includes the cosmological constant and the coupling constant with Weyl tensor and the copies of the matter and 2 copies of the stress energy tensor aa gaya. Actually, the curvature tensor with the 2 copies of the stress energy tensor represent the source term coming in and coming out and interacting with the gravitational field, because the Weyl tensor C alpha and beta nu represents the pure gravitational field aa gaya. Kadir, Lee, and Kim provided the equation of motion, provided this equation of motion aa gaya, which is shown in blue aa gaya. Now we could draw a graph between the tangential velocity curve and this vector r, where lambda is the central density. Now, first of all, we draw a plot for M31 galaxy to explain the velocity rotational curve. Here rho is the central density of the M31 galaxy and lambda is a coupling constant that we will determine. Now we discuss the nature of galactic halos and the future prospects. Kadir and Lee consider the velocity rotation curve for a simple model for different values of the coupling constant. Now we are determining the value of this coupling constant that describes the velocity rotation curve of the M31 galaxy and the Milky Way, as if suggestion will seem consistent, bearing minor adjustment in the matter distribution in the galaxies and so on.
Thank you, Mohammed, for your talk. Even if the audio was not very good, at least on my computer. Any questions? Mohammed, you can share your screen. It's not needed that.
Yes.
So you think that you are able to fit or to reproduce the velocity rotational curves of galaxies without dark matter, but just with this modification of gravity law?
Einstein-Hilbert Lagrangian.
Okay, it's interesting. Okay, then we arrived, at the end of the session. I don't know if, so you can, Mohammed, you can share your screen so that
Yes,
we can see the participants.
yes, sir. I am sharing my screen.
No, it's still shared. As I don't know if I can do anything, for example. How I can, because I see your screen shared. It appears that your screen is shared. I cannot do anything. I don't know why. I don't know, Asghar, if you can stop. Okay, okay, now it's okay. Because Asghar, you are the host and you have more power than me. Anyhow. So any comments about at the end of this session? It is clear that there is much more baryonic matter than we can actually observe, and it's very hard to find where the missing baryons are. And I think, but we are going towards the good direction. I don't know, Asghar, if you can just make some final comments.
I think there's no other comments, no questions, then we can close the session.
Okay, well, then I would like to thank all the speakers of the session, both the invited speakers and the normal speakers, let's say. Thank you very much. I mean, all talks have been
thank you, everybody.
very interesting. Okay.
Thanks again to the organizers for this wonderful session.
You're welcome.
Thank you, organizer.
Okay. Thank you to everybody and goodbye.
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 Thank you again. Bye-bye.
Bye. Yes.
Bye.